All right, so this is listed as the kinetic molecular theory makes some assumptions. But this is kind of a headline version of that, a bulleted version. In fact, I have bullets here. Okay? If you go back to page 15, there's more detail. Yeah, there's more detail on page 15. Okay? So, you need to study this, but use page 30 perhaps to help you memorize. But you can't just memorize 30 and expect to really understand. This is the headline version. When you see the headline, you've got to know, or need to know, what else goes along with it. Because you have to understand the kinetic molecular theory, not just be able to repeat, 5 bullets, okay? Yes. Yes. Okay. All right, so let's talk about them for a minute, all right? Very often we say, let me tell you about this first. The kinetic molecular theory of gases is what basically defines ideal gas behavior. It defines ideal gas behavior. It defines ideal gas behavior. Okay? Now what you're going to find out as I discuss this, if you're listening, if the gears in your brain are turning, okay, if you're actually focusing, is that there is no such thing as an ideal gas. All right? So that should seem a little bit crazy. But here's the reason. Well, we're going to find out more about the reason. Basically, what we're trying to do is to make the math easier when we can make it easier. Okay? That's what it comes down to. And unless we're dealing with certain extreme conditions, we can do the easier math. But to do the easier math, we have to make these assumptions about gases, treat them like ideal, even though they really can't be ideal. All right? Well, you with me so far? Have I thrown you too far yet? Giving you too much of a curve? Everybody struck out so far? All right. Let's talk about some of these. 5 assumptions of the kinetic molecular theory as it applies to ideal gases. And remember, there are no truly ideal gases. The gas consists of very small particles, each of which is so far apart from the next, we can treat the particle as if it only has a mass or weight, but no volume. And on page 30 it says the particles have mass but no volume. Okay? But what it says here is we can treat it that way. Now, is it true that a gas molecule can have mass and no volume? No. It's not possible. All matter has to have what? 2 things? Volume and mass. Okay? So it wouldn't be matter if it didn't have volume and mass. Well, we treat it like an ideal gas particle. Okay? Well, the reason we can treat it that way is that the size of the gas molecule is so small compared to the vastness of the distances between the gas molecules on average that it's just inconsequential. It doesn't. If we were to include the gas particle volume in our calculations, it would be such a tiny number, we'd have a really, really long decimal number, and we'd round off the number anyway. So it wouldn't matter. Okay? Let me give you an example of an inconsequential measurement. Okay? Everybody stand up. Everybody stand up. And face the back door going to the hallway out there. Face the back door going to the hallway. All right. I want you to take one baby step toward that door. All right, one baby step. There you go. You are on your way to Greenville, South Carolina.
No.
Yeah, that's generally the direction of Greenville. Guess what? Guess what? Does it make much difference, that baby step? No. Not much.
No.
That's right. Not. Yeah. All right. So that one baby step is inconsequential. Does that make sense? Likewise, in the same way, the size of gas molecules is so small, they are inconsequential to the measurements we are going to be making here that matter. All right? If you've got to travel 30 miles to Greenville, one baby step, that ain't much, is it? Doesn't really get you there very fast. Okay? Have a seat.
That's one that's wood, though. I thought Greenwood. Greenwood on it. Yeah.
No, that way's Woodruff. That way's Greenville.
Woodruff's down here. Greenville's over
I know
here.
You got to remember the way the building is oriented, I suppose. But I know. Not right now.
Can I go and get that?
Yeah. If you will take the bathroom pass and sign out and sign in
I'll sign out.
and take the bathroom pass. All right. Collisions of gas particles. It says they're perfectly elastic. All right. If I take a ball, any kind of ball, no matter what kind, golf ball, I drop it from right here. Where's it going to bounce back to?
Not all the way.
Not all the way. The reason it doesn't come back to my hand when I drop it to the floor is that it loses some energy when it hits the floor. Some of that energy is turned into heat due to friction when it hits the floor. The ball is warmer, the floor is warmer right there. Now sometimes it's so little change in temperature you can't measure it, but the heat's there. Okay? So that if it were perfectly elastic, it would come back to where my hand is. Okay? And you can't do that. It's not possible. But the amount of energy lost in that collision between gas molecules or the surface of a container holding a gas is so small compared to the other behaviors that we're going to measure and be dealing with in here, they really don't matter. Okay? Again, if we included that lost energy, it would be decimal places way out here. We'd round them off anyway. They don't matter. Does that make sense? So all of these things are fit in that same category. The effects are actually there. They actually exist, but they're so small, they're inconsequential to the kind of math we're going to do in this class. All right? So molecules are in constant random motion. Well, sometimes there's a molecule that isn't moving. Very rarely, but that's pretty close to being true. There are no forces of attraction between gas particles. Well, you know that can't be true. We've already been figuring out about the way that gas electrons shift around, either permanently or temporarily, creating polarity. So gas molecules have to have stickiness. If gas molecules didn't have stickiness, airplanes wouldn't fly. Okay? Why is that true?
You said what? You said gas particles in that stickiness.
That's right.
Explanation, please.
Well, it's the way that the wing of the airplane cuts through the air. Okay? And the stickiness of those molecules actually pulls the airplane wing up. Okay? Huh? Well, it's sort of gliding. I mean, it's being pulled by the engine, but it's sort of climbing up to the air, yeah. It's kind of like you swimming in the water, only it's using air instead. Okay? Well, but it's the stickiness of the molecules that causes that behavior to occur. You okay? I mean, you don't have...
What about when it rains?
Huh?
Do that affect the stickiness when it rains?
Say again?
When it rains, did it affect the stickiness?
Somewhat, but it's not enough to make the plane fall down or anything, no. Okay? But if you start deforming the shape of the wing by adding ice, icing becomes a problem, and then it could fall down. Okay? Huh? Partly it's due to the weight, and partly it's due to the deformation of the wing surface. Okay? Part of the reason a plane flies is because you're piling up air molecules on the bottom and they're pushing apart. And that pushing apart, okay, is not force of attraction either. That's a repulsion. All right? So, and then on the top, you've got a pulling effect due to the stickiness of those molecules. So you got two different kinds of forces going on at the same time, causing an airplane wing to fly. That's the model. Okay? That's the model. That's what scientists who study such things believe is going on based on the experiments they've conducted. Okay? Average kinetic energy of gas molecules depends only on the temperature of the system. Well, temperature isn't the only thing that affects it. Momentum is really a better way of determining kinetic energy. But because most gas molecules are so far apart, have a certain really, really small mass, we can ignore the mass of the molecules in terms of determining kinetic energy. We can use only temperature to do that. Okay? Again, it's a matter of degree. Really small amounts don't matter much in the big picture in this case. All right? Does that make sense to everybody? Okay? So the reason, now, as long as we make these assumptions about gases, then all gases will be ideal. But there are no truly ideal gases. We treat them like ideal because it makes the math easier. Does that make sense? Now, here's when you can't. This is important. This is when you can no longer treat gases as if they're ideal. You cannot treat gases as if they're ideal when you cannot treat gases as ideal when they're under extremely high pressure or extremely low temperature. I'm sure it is. But the more times you're exposed to it, including the times you write it, the more likely you are to remember it. If you aren't practicing by writing down notes, you're practicing to fail. Really, really, really high temperature or low, really, really high pressure or low temperature. Yes.
Have you been practicing stuff, or you just doing it?
I've been working on it for some years. Yeah, it is. Yeah. All right. Now here's what you need to know about this. Now look. All of the gas laws we'll be doing math with in here are based on the idea that we are dealing only with ideal gases. All of the gas laws we're going to be working with in this class are based on the concept of ideal gases. So we're not going to be dealing with extreme temperatures, extremely low temperatures, or extremely high pressures. Okay? Because then we'd have to take into account gas volume. We're only going to be dealing with gases that we can treat like ideal with the math we're dealing with in here. Okay? Any questions about that? All right. So let's start then with Charles' law. Let's start with Charles' law. Okay, so what Charles figured out is that, No, Charles had one law. You got Boyle's law and you got some other laws too. Okay? Charles figured out this, that as long as the pressure isn't changed, as long as the pressure is not changed, and as long as the amount of gas isn't changed, if you change the volume of gas, the temperature will change in the same way. As long as you don't change the pressure or the amount of gas, if you change the volume of gas, the temperature will change in the same way. The volume, if you change the volume, the temperature will change in the same way. And conversely, if those same conditions hold true, that is, you don't change, there's no change in pressure, no change in the amount of gas, then if you change the temperature, the volume will change in the same way.
If you change the volume, the temperature will change.
They'll change in the same way. What do I mean by the same way? The same way means if volume goes up, temperature also goes up.
Is that why, like, when you go basketball outside in the sun, and you get a bounce, it feels like it's more inflated?
Yes, that's exactly right. Only really what's happening inside the since the basketball doesn't really change its volume, you're really dealing with a different law altogether. And that's where,
The pressure inside.
Yeah, this is pressure goes up, temperature goes up. I mean, temperature goes up. Yeah, if pressure goes up, temperature goes up. That's what that is. Okay, so that's Gay-Lussac's law. We don't deal with that in here. Okay.
The other way around.
If the temperature rises and you don't change the volume, then the pressure is going to go up. Yep.
You see, if the temperature goes up, if you don't change the volume, the pressure will go up.
Yeah, but you don't need to know that because that's not one of the laws we deal with in here. I'm just answering his question. Okay? All right. Well, so we can write this in this fashion. If they're changing in the same way, then if I put them in a fraction like this, they're going to equal a constant. That's the nature of Charles' law. There's a better way to write it when you're doing calculations. Okay? So if I have an initial volume and an initial temperature of something, and I increase the temperature, well, because it's always going to equal K, the new temperature and the new volume will also equal K, so they're equal. And this is the way we write Charles' law most of the time. Most of the time we write Charles' law like that because that's the way it's most practical for solving problems. Okay?
You do it as a proportion like when you're solving.
Say what now?
You do it as a proportion when you're solving it. Like you would have 3 of them and you're trying to find the fourth one.
Yes. All right. However, there's a couple things you need to know about this. One is you may have used cross multiply and divide in math, but not in here. We are not going to be doing cross multiplication and division in here. Okay? There's a reason for it, and it's going to really mess you up if you try. No, I won't show you how to do it. I won't give you a process for doing it. All right? No, don't put in a triangle. We're going to have equations that are too complex to use that process. And if you try to use that process, I've never seen anybody try to use that process on a more complex equation and get a right answer. Never. So I'm outlawing it, okay? So we're talking about laws. We're going to outlaw it, all right? Because we want to try to get you to where you can get the right answer. So I'm going to back up a little bit. We're going to use math the way it was, the way that cross multiplication and division was designed is a shortcut for what I'm going to teach you. So I'm going to teach you the long way because it works every time. Cross multiplication and division only works in certain cases, and you got to know when they work. And too many times it just goes all haywire for you, okay? Huh? The long way is the safer way. And in here I want you to get a right answer, okay? All right, it's not that much harder, really. All right, let's look at what we're going to do. All right, let me give you a problem, all right? Let's suppose we have a volume of gas that's 2.5 liters, okay? We got a volume of gas that's 2.5 liters. And that volume of gas is held at a temperature of 300 K. So I'm going to write this out so you don't have to change the temperature, but we'll talk about that in a minute. Okay? And I want to change the temperature. So this is going to be a first temperature. This is going to be a second temperature. We'll change that temperature 350 K. Notice I put a decimal place right there. That means those zeros are going to be significant when they wouldn't be otherwise. Remember that? From Unit 1? Okay. And as a result of that temperature going up, what's going to happen to the volume? It has to go up. So that's at volume 2. We don't know what it's going to be. This is volume 1. Okay? Now, when you solve these gas law problems in this class, I expect to see a list of knowns and unknowns. You will get credit for writing a list of knowns and unknowns. Okay? This is going to be how you're going to get these gas law problems right, is by writing the list of knowns and unknowns every time. We're going to practice with some simple stuff, so when we get to the complex stuff, it's sort of old hat and it's easier, okay? All right. All we have to do then is plug in the knowns and unknowns to this equation. Later on, you've got to figure out what equation. But look at here. Looky here, okay? It practically tells you what equation to use, doesn't it? What other equation is there besides Charles' law with these variables? That makes sense? Volume 1, temperature 1, volume 2, temperature. That's got to be Charles' law. Okay? All right, so let's plug in our values. So we got 2.5 liters. We're going to plug in 300K for T1. We're going to plug in 350K for T2. Kelvin. And we don't know what volume 2 is going to be, so we're going to leave that alone.
Ain't Kelvin like really, really hot?
No, Kelvin's just a different way of measuring it.
What's the official?
Huh?
What's the official?
There is no official way. This is actually the best way. All right. Now, to solve this problem, we want to first start with isolating the unknown. Well, here's your unknown right here. And we're going to isolate it by doing the math on both sides exactly the same. Whatever you do to one side, you do to the other, you're going to get that's still going to be an equality. So the way we get the V2 by itself is we multiply both sides by 350K over 1. As long as you do it to one side, as long as you do it to both sides, it doesn't change the fact that it's an equality, and it's going to isolate the unknown. So all of this is going to cancel. We've got V2 by itself. We're going to cancel K here. Look, that's going to cancel. What's left in units?
2.5 liters.
In just units, it's liters, and that measures volume. So we know we've set it up right. Okay? And now all we have to do is multiply this times this, hit equals on your calculator, divide by this, hit equals again, and you got your final answer. Okay? So please solve that problem. All right? Solve that problem. Okay? Please get your calculator out and solve this problem. What do you mean, the final answer? Well, you can finish it at home. It's just solve the calculations here. Y'all got to go, so y'all can solve it at home. Okay, just bring it in, solve tomorrow. All right. But everybody else, other than the people that are going to RD, need to solve it right now.
3.25.
Huh?
3.25.
3 point.
Just kidding, don't write it.
All right. Well.
350, 2.5, right?
Right, and then you're going to hit equals and then divide.
Well, we say do what?
You put 350 times 2.5, hit enter. Then you hit your divide button, put in this number, and hit enter, and that'll give you the answer. Okay?
Like 195.
Okay, Ben, what'd you get? Full answer. Huh?
3.916 repeated.
916 repeated or 16 repeated?
916 repeated.
The number 6 repeated.
2.916666, that?
Put a line over it.
Put a line over it.
Put a line
Put a
over it.
line over.
And there's a 7 at the end.
Two more six, yeah.
All right, that's liters equals V2. And round it off to how many digits?
That's incorrect.
No, about.
I'll tell you.
That's incorrect. It's the same thing.
3, 4.
No.
I mean, 2.9, my bad.
2.9.
Three significant digits.
2 digits. 2 digits.
What about the 3 9?
That's 3 significant digits.
2.9.
We want the one with the least digits. That's how we find our final number of digits.
Oh, yeah.
2.9 liters equals V2. All right. So we're not going to use cross multiply or cross divide. What we're going to do is we're going to isolate the unknown instead. Okay? All right, now, one more thing. We don't pack up yet. Hold on. All temperatures in gas law problems must be Kelvin temperatures.
So I would just take
All temperatures must be Kelvin temperatures. You need to get out your test references if you don't have them out. All temperatures must be Kelvin temperatures. Get out your test references. Huh? Oh, yeah. But this is an easy conversion. All right? Get out your test references. Listen, please. Get out your test references. And find this sheet right here. The one that has your solubility rules? Okay. There's Charles' law right there.
I see that thing.
Okay. I'm not telling you what the name of it is, but there it is. Now look. There's your conversion between Celsius and Kelvin. So if I ever give you the temperature in Celsius, you add 273.15 to it, following the rules of rounding and everything that I've given you to get the Kelvin temperature. Okay? So you add 273.15 to Celsius, you subtract 273.15 from Kelvin to get the Celsius temperature. Okay? Does that make sense to everybody? All right. Listen while you're packing up. Listen while you're packing up. Shh. You are supposed to be annotating and studying your unit handout. Make sure you are studying your unit handout. Just reading it, just marking things isn't helping you much.